process by a chemical reaction. Okay, so we are going to read here whatever are the heat exchanges happening in a chemical reaction. Now, to know about the heat exchanges there, we need a device, right? So a device in which all these heat changes are observed, that is basically your calorimeter. So let us write down one statement about it. So it is a device used to measure heat of any reaction, any chemical reaction. Okay. Now the thing is, there are two types of calorimeter here. Types of calorimeter. In that, we are having two types. One is constant volume calorimeter. Constant volume calorimeter. And specifically in that, we are going to read about bomb calorimeter. And the other one will be basically your constant pressure calorimeter. I am leaving one line here. One is constant pressure calorimeter. Sometimes it is also known as coffee cup calorimeter or else that kind of arrangement. Now if I ask you heat exchange at constant volume, heat exchange at constant volume, that means I am referring to QV. Heat exchange at constant volume, whether it is delta H or delta U. Heat exchange at constant volume, is it delta H or delta U? Heat exchange at constant volume. Delta U, good. So heat exchange at constant volume is delta U. So when I am having a calorimeter which is being operated under constant volume, that whatever is the heat exchange happening, I'll be able to get delta U from there, right? Similarly, if at all I ask you what is heat exchange at constant pressure, so your answer would be here delta H, right? So that means what? Using this calorimeter, that is constant volume calorimeter, I'll be able to calculate delta U of any reaction. Using constant pressure calorimeter, I'll be able to calculate delta H of any reaction. Okay. So I'm going to write down that only. Used to measure delta U of any reaction. R stands for reaction. In fact, I'll write it down here. Delta U for any reaction. So you should understand like this. Heat, that internal energy change for a reaction, right? That's what we are measuring here. Now, similarly, I can write down here, this is used to measure delta H for the reaction. Again, R stands for that. So, enthalpy change in any reaction, internal energy change in any reaction, we'll be able to calculate from these two. Okay. First, finish writing this quickly, then we'll proceed further. Completed? Good. Now the thing is, let us proceed towards the first one, which is constant volume calorimeter. This one is your bomb calorimeter. And we are going to first draw a diagram here. So all of you can draw the diagram. You are having a steel vessel or bomb, right? Around it, basically we are going to fill up liquid here. And around this entire thing, we are having insulation. Then, this is where it is standing here actually. A small cup where we will be keeping the substance which is to be combusted, oxygen gas. Then we are providing some ignition wire here. Right, water is filled up here. And then you are having a thermometer here. One mechanical agitator. So let us just label it. This is ignition wire. Ignition wire. Insulation here. thermometer which you are able to see. Here H2OL. This is bomb or else steel vessel whose volume will not change when the reaction is going on here. This one is substance to be combusted. Substance to be combusted. And this one is like calorimeter bucket actually, but I am simply writing this as calorimeter where you have filled up water. This is your mechanical agitator. Right? So simply write this out, draw this out, then we'll proceed further. Once you are done, then we'll understand there what is happening. Once you are done drawing, let me know. Then put a thumbs up there so that I can come to know, okay, people have drawn that. Okay, now let us understand what is happening here. See, first of all, we are calling this as a bomb calorimeter, and you are able to see this is a small vessel where reaction will be happening. That vessel is known as bomb, right? And here the vessel volume will not change when the reaction will be going on, okay? Now, the other thing is, this one you are able to see around this bomb, you are having basically what? You are having one big vessel here in which we have filled up water. So basically that is calorimeter bucket we say, but for simplicity we are using the term calorimeter. So calorimeter system if I say, so that will be bomb plus the water around it, okay? Now before starting this reaction, we would have measured the temperature, initial temperature of this water around this bomb, and let us say that is T1 temperature, okay? Now tell me if at all, here we might take any substance, right? And here we can carry out any reaction, but for simplicity's sake, we are going only for the combustion reaction for better understanding, simple understanding, right? So for combustion, let us say we are having, we have taken some amount of, kind of maybe 10 gram, 20 gram, 10 mole, 20 mole of it. So I'm saying I have taken n mole of a substance here, right? And I'm trying to do its combustion. Now how combustion will be done is, basically first of all you should understand around the equipment we have put the insulation so that no heat is going out of this system here, right? And the thing is we have provided ignition wire. What is the role of that ignition wire? Just for initiating the reaction, you need to give initial spark there. Electrical spark you need to pass on so that the reaction can start off. Okay. And once the reaction starts off, it will be self-sufficient to go on its own, right? Some amount of oxygen is also trapped there because we have to carry out combustion reaction, and for combustion we require oxygen, right? Now the thing is, here we have taken basically the substance to be combusted, oxygen gas is also there. Now the thing is, when I ask you whether combustion of any substance, is it exothermic reaction, endothermic reaction? Is it endothermic or exothermic reaction? Combustion. Somebody is asking me why it is a bomb calorimeter. And what answer should I give you when I have drawn that already? Heights of asking the question, beta. It is labeled here bomb and a calorimeter, then also why calorimeter? It is exothermic reaction, right? So the thing is, you should understand when the combustion reaction will start. So the thing is, whatever is heat liberated, it will first warm up or heat up the vessel surface, bomb vessel surface, right? And then the heat is going to travel up into the water. So the temperature of water is going to rise, okay? So when the temperature of the water rises, that will be recorded in this thermometer, okay? Now the thing is, After some time, you will see that the thermometer is not showing any reading. What does it mean? That the reaction here is completed, equilibrium is set up inside. That's the reason there is no heat flowing from this bomb into this particular water. Okay. So at that time, whatever is the temperature recorded, that will be final temperature, which is T2. So T2 minus T1, you will get your delta T. Now, ultimately, what is the principle lying here is that whatever is the amount of heat released by this reaction, that will be gained by this bomb as well as by the water, and bomb plus water is basically your calorimeter system. Now here some might wonder why agitator is provided. See, if agitator is not there, then the heat will not be kind of distributed uniformly. So to have that uniform temperature of the water, agitator is provided. Okay. So now let us go further here for writing the things. So here I can simply write down heat released due to combustion of n mole of the substance, that is going to be equal to heat gained by the calorimeter system. Heat gained by calorimeter system. Now when I refer to calorimeter system, I am referring to H2O plus the bomb there. Both of them, they are making the calorimeter system. Now applying the sign convention, heat release will be minus Q and combustion is a reaction. So simplicity, I am writing minus Q reaction. That means heat released during the combustion reaction of n mole of the substance. Heat gain means positive, it will be who is gaining it? Calorimeter system. Calorimeter system. Now, do you recall that we have written heat capacity as dq upon dt, and from there I could write down q is equal to C delta T. So in place of q calorie system, what I am going to write down is, I am going to write down simply q reaction minus, I am shifting that side, minus C delta T for the calorimeter system. For the calorimeter system. Did you understand till now what we are doing? Simply we are applying the principle of calorimetry only. Heat released by that chemical reaction, it is being gained by the calorimeter system. And then I applied the sign convention. Written there, can we proceed further to the next slide? Okay. Now, next thing is, always remember delta U is defined for per mole of a substance, right? Now the thing is, we are saying n mole of the substance is undergoing combustion. So for n mole of substance, you are having Q amount of heat. So for 1 mole, it will be Q by N. That's the reason I have written delta U is equal to Q by N. So ultimately the formula will become delta U here, that will be equal to minus of C delta T for the calorimeter system divided by N. And this is your main formula which you have to remember. Right? Where what is the C? C is heat capacity of calorimeter system. Heat capacity of calorimeter system. Sometimes they may simply write down heat capacity of calorimeter also, one and the same thing, right? Now, do we know that in this calorimeter system, I have, kind of included water as well as bomb. So sometimes it may be possible the examiner is giving you different heat capacity for bomb and different heat capacity for water. That means segregating that system. Otherwise, main formula you should treat, this is only the main formula. Now in that case, the formula will become what? Delta U reaction, that is equal to minus of C delta T for water plus C delta T for the bomb. This divided by N. Are you able to understand what I've done? Simply I am segregating depending upon if the examiner is giving heat capacity of water separately and heat capacity of bomb separately, which is a rare case scenario for you, right? But still I am giving you the formula. Are you able to understand what we have done here? Is there any doubt to anybody? Now for water, the examiner may give you specific heat capacity or else may give you molar heat capacity. So depending on that, little bit modification will come in the formula here. So which I am going to write down. If for water, specific heat capacity is given. Do you remember we have written specific heat capacity is heat capacity upon mass. So C should be replaced as MS. Are you able to understand? If at all specific heat capacity for water is given, we know specific heat capacity is heat capacity per mass or else per unit mass here. So simply formula will become delta U reaction, that is equal to minus of MS delta T for water plus C delta T for the bomb divided by N. Is there any trouble here? I am simply modifying the formula. There is only one main formula where I have put triple star there. You have to remember that only. Getting it? But in your knowledge it should be there. Okay, this could also be the form. So if for water, suppose Cm is given. Cm means molar heat capacity is given. And do we know that Cm is heat capacity per mole? So you are writing C is equal to N into Cm. So the formula will become delta U for the reaction, that is equal to minus of NCm delta T for the water plus C delta T for the bomb divided by number of moles. Is there any confusion to anybody? See, simply if at all you ask me to remember one particular formula in calorimeter, simply remember delta U is equal to minus C delta T of the calorimeter system divided by N. That's your main formula. And why I have given you rest of the formulas, if examiner gives you heat capacity of water separately, heat capacity of bomb separately, then please separate that system and you can write it. Are we getting it? And it could be possible that rather than giving you heat capacity, specific heat capacity is given, right? And specific heat capacity, in that case, C should be replaced by S. Molar heat capacity, then it should be replaced by N into Cm. Is this point clear? Then we'll be going for solving some question here. So main formula you simply treat it as minus C delta T upon N. We'll solve the question, you'll understand it more in a more better way. Have you finished writing? Let me know. Then I'll give you one question which you try it out. Okay, now let us go for a question here. I am giving you 0.16 gram of methane was subjected to combustion in a bomb calorimeter, at 300 Kelvin. The temperature of calorimeter was found to rise by 0.5 degrees Celsius. Calculate heat of combustion. Calculate heat of combustion. First one at constant volume. Second one is at constant pressure. Given heat capacity of the calorimeter system is 17.7 kilojoule per Kelvin. And I am giving you a note here that will definitely help you out. Heat of reaction at constant volume. In fact, all of you know this. That is equal to delta U. And if at all they are asking you heat of reaction at constant pressure, so you're going to write down delta H. So first of all, you calculate delta U because heat of reaction at constant volume I have asked Everything is given to you very clearly. Go for it and let me know the answer. For delta U, what will be the formula which you are going to use? Plus or minus, Kaushik? Plus or minus? That's what is my question. Correct. See, the thing is, things are very simple here. They have given you 0.16 gram, right? So first of all, find out the number of moles of CH4, because in that formula, N is what? Number of moles of the substance which is undergoing combustion. So here, mass upon molar mass, you will be having 0.16 divided by 16, which will give you 0.01. Now, next we know delta U is what? Minus C delta T upon N, and C delta T for the calorimeter system. Right. And do remember, this is number of moles of substance undergoing combustion. Undergoing combustion here. So simply all the things are given to you. Here I'll be writing this as minus of, you are having 17.7 kilojoule per Kelvin, 0.5 is the change in temperature, number of moles is 0.01, so you are writing here minus 177 into 5, which will be minus 885 kilojoule per mole, right? No, Bhavani, check your calculation there. Little bit silly mistake you have done in decimals. Right? Now the next thing is, I have asked about delta H. Now for delta H, for any reaction, what is the relation between delta H and delta U? Vishesha, check your answer. Second answer is wrong, beta. So the thing is, for what is the relation between delta H and delta U for a reaction? Delta H is equal to delta U plus delta Ng RT. So what we are going to write down here is, first of all, for calculating that delta H, we have to write down basically equation, combustion equation of methane. And in this case, water we are going to write down as liquid or else gas. Water should be present as liquid or gas, tell me. For this combustion, CH4 plus O2 gas giving you CO2 gas plus H2O, L or gas, liquid, because the temperature is 300 Kelvin. Around room temperature, water is liquid. You know? So the thing is, just balance it out here 2, here 2. So delta Ng will be 1 minus 3, which is minus 2. After that you apply delta H is equal to delta U plus delta Ng RT. Delta U have calculated minus 885. Remember, this is in kilojoule. Because the thing is, if at all you do not remember this, then you are going to make grave mistake, because R value you take it wrong, right? This one is minus 2, 25 by 3 into 10 to the power of minus 3. Temperature I have given you 300. So overall you will be getting 5 from here. So basically minus 885 minus 5, you will be having minus 890 kilojoule per mole. Are we able to get it? Right? So the problem is very simple. There is one more question for your practice in NCERT. One solved example is there. In fact, that is much more simpler example, because they have given you combustion of 1 mole of carbon graphite. So simply the equation will be like this only. They would have given, basically they are asking you delta H. So first find out delta U. Delta U will be minus C delta T upon N. 1 gram means number of moles will be 1 by 12. Put here 1 by 12. Delta T, I think they have given you change by 1 Kelvin. C also mentioned. So you'll get delta U, and since delta Ng is 0, so delta H will become equal to delta U. Are we able to understand here? Chalo. Now let us go for the next here, which is constant pressure calorimeter. And in constant pressure calorimeter, Definitely here volume can change, but the thing is pressure cannot change. So something like a movable piston system kind of, equipment could be there where you are doing the combustion. And only thing is whatever are the heat exchanges happening, they are happening at constant pressure. So simply heat exchanges at constant pressure, that will be equal to delta H. And in the previous equation what we have written, or else in the previous case for constant volume, we have written heat exchange at constant volume is equal to delta U. Here heat exchange at constant pressure will be equal to delta H. And what was the ultimate formula which we derived in the previous case? Delta U is equal to minus C delta T upon N. Here we will be just replacing delta U by delta H, nothing more than that. Okay. So here we are going to write down whatever is the heat exchanges at constant pressure in any reaction, that is known as delta H for the reaction, and delta H for the reaction is equal to minus C delta T, and this is for calorimeter system upon N. Right? Again, N is number of moles of substance undergoing reaction, and that reaction could be any reaction, be it combustion or anything else. As such, majority of the time examiner will be giving you bomb calorimeter only. I have not derived this, I have given you directly formula there, because the thing is, only thing is their constant volume was there, here constant pressure. Can we proceed further? I'll give you one or two numericals here. Let us go for the complete combustion of ethanol in a bomb calorimeter, 1500 kilojoule of heat is released at 300 Kelvin. Calculate delta H for the reaction. Please calculate this, everyone. And one must know that around this temperature, which is around room temperature, ethanol exists in liquid or gaseous phase. Liquid or gaseous or a solid, which phase it is existing? Around 300 Kelvin, which is your room temperature. And you have to keep your answer in kilojoule if you are answering liquid, correct? So the thing is, here C2H5OH liquid plus you are having O2 gas giving you CO2 gas plus H2OL. Simply balance it here 2 and here it will be 3. So delta Ng will become 2 minus 3, which is minus 1. Solve it, everyone, and let me know the answer. Is there any answer here? See, the thing is, you have got this value, and one more thing is, they have given you that this much amount of heat is liberated, and they have mentioned bomb calorimeter. That means what? Volume is constant. So whatever is this heat exchange at constant volume, that is delta U, but mind well, you have to take minus 1500 kilojoule because heat is evolved. Did you understand this? Because from the question you must be able to identify whether it is delta H or delta U. No, Pavitra, some mistake you have done, beta. Now the thing is delta H is equal to delta U plus delta Ng RT you have to go for. Delta U is minus 1500, delta Ng is minus 1. R value you remember carefully, 25 by 3 into 10 raised to power of minus 3 for kilojoule per mole Kelvin. And 2 kilocalorie, that means 2 into 10 raised to minus 3 kilocalorie per mole Kelvin. Right? So here I'll be taking in kilojoule, that means 25 by 3 into 10 to the power of minus 3. This is 300. So I'll be having this entire thing will be 2.5. So ultimately I'll be left out with minus 1502.5 kilojoule. That is your final answer. Yes, majority of you got it. Very good. Sai, Hemashri, Ganesh. Vishya, you are little bit in hurry burry beta and a silly mistake. Do not do that silly mistake. Questions are very simple. Hopefully it is clear. Now let us go for the next question. I am writing here 80 kilocalorie of heat is absorbed when 2 mole of water is vaporized. 2 mole of water is vaporized at 300 Kelvin, 1 atmosphere pressure. Find delta U and delta H for this change. Now I am not going to solve. Yes, Pavitra, good. Identified your mistake, na beta. Now the thing is, I am not solving this entire question, but there are certain basic fundamentals which I am going to ask you so that it will be helpful for analyzing the problem, right? Now in this particular question, by reading what you are able to see is 2 mole of water is getting vaporized. That means reaction is H2OL getting converted into H2OG. Now I told you that when you have to calculate delta Ng, make sure that you are having same number of moles of that reactant reflected in the reaction. That means you multiply here by 2 so that you are having 2 moles of water getting vaporized. So that delta Ng you do not forget. So what I'll be writing here, 2H2O liquid, which is giving you 2H2OG. Is this digested by everyone, what I've written on the board? 2H2O liquid giving you 2H2OG. Now, so this will imply that delta Ng is going to be 2. Right? Just to make sure that you never commit mistake for delta Ng value, that's what I'm saying. Whatever is 2 moles, it should be 2 moles of water here. Right? Now the other thing is this a phase transformation? Is this a phase transformation? Write down yes or no, right? Now, if this is a phase transformation, then we know that phase transformation happens at a particular temperature and pressure. Now, do we know heat at constant pressure and do we know heat at constant volume? So, if at all I am saying here, pressure is given to you, right? So, this 80 kilocalorie is heat at constant pressure. So, the thing is, it is given Qp is equal to delta H, which is equal to plus 80 kilocalorie because it is absorbed. Did you understand why did I take this as Qp not as Q delta U? Because there was no hint about bomb calorimeter or else closed rigid vessel or else volume constant. This phase transformation happens at constant pressure and at a given temperature. Are you able to understand? Right? Now can you find out delta U from here, everyone? So delta H, you got the answer. It is 80 kilocalorie. Find out delta U. Keep your answer in kilocalorie itself. And again, be careful with the R value. Majority of the time you people are committing mistake there only. See again, mistake only. 2 answers I have got, mistake only. Kaushik, check your answer. Sai, you also. Manas, something is what? Plus or minus, beta? I think you are almost correct there. Those who are answering 78.8, absolutely correct. Shankar has answered, Vishesha has answered, Manas also. Good. Pavitra, you are getting 75 because you have taken R value as 25 by 3 into 10 to the power of minus 3. One side kilocalorie, another side you are having kilojoule. Do not do those blunders there. Now the thing is, here you will be writing delta H is equal to delta U plus delta NGRT. Delta H is 80 kilocalorie, delta U you have to find out, delta Ng is 2. Kilocalorie means 2 into 10 to the power of minus 3. Temperature I have given you 300. So this entire thing is 1.2. So you'll be writing delta U is equal to 80 minus 1.2, which is 78.8 kilocalorie. So those who got 78.8 kilocalorie, wonderful, good job, right? Understood this? Can we go for the next question? All the questions are very simple. Only thing is your silly mistake, your less attentiveness is causing the mistake. I'm giving you another question. 100 kilocalorie of heat is released when 2 mole of benzene is burnt in excess of oxygen in a closed rigid vessel at 300 Kelvin. Find delta U and delta H for the reaction. Pay attention here properly, whatever I have written. Closed rigid vessel also. नहीं मेरा 125 तक है।
लीजिए ना। अच्छा सॉरी मुझे लगा खाली है, मैं तो ऐसे ही टाइम पास करने आ रहा था।
Now here you understand one thing, what is given to you is 100 kilocalorie of heat is released. Is it delta U or delta H given to you? In a closed rigid vessel you are carrying out the reaction. That means it will be delta U. So the thing is QV is equal to delta U, which is minus 100 kilocalorie. Now next thing is you have to go for C6H6 liquid plus you are having O2 gas, which is giving you CO2 gas plus H2O liquid. Now the thing is here it is 6, here it is 3. When you balance it, it will become 15 by 2. But you don't stop here because I have given you 2 mole of C6H6. Yes, Hanudeep, very correct. Correct, absolutely correct. Wonderful. Now the thing is you will be writing here 2C6H6L plus 15O2G. You will be having 12 CO2G and you will be writing 6H2OL, right? Now in this case, this reaction you have to go for because in this you are able to see 2 moles of C6H6. Are we getting it? So from here you find out delta Ng 12 minus 15, which is minus 3. Otherwise some of you might have got answer as minus 100.9 also, which is wrong. So the thing is you go for delta H is equal to delta U plus delta NGRT. Delta U is given, which is minus 100. This one is minus 3 for kilocalorie, 2 into 10 raised to the power of minus 3. And you are having here 300 Kelvin, which gives you, this one is 1.8. So ultimately you will end up with 101.8 kilocalorie. That is your answer. Are we able to get it? Now let us go for one more question here. For the given reaction at 300 Kelvin, 2A gas giving you 3B gas plus C liquid, delta H is 100 kilocalorie per mole. Find delta U for the reaction when 0.5 mole of A reacts to form products. Reacts to form products. Calculate this quickly, all of you. Yes, Gautami, correct, beta. No, Vishaya. Vishesha, no, beta. That's wrong. Vishesha, that's wrong. Here I'll tell you. The thing is, you are having 2A gas going for 3B gas plus C liquid. Now, what I told you, basically I told you that you should see 0.5 moles of A here. So for that, if you multiply by a factor of 1 by 4, then 2 by 4 will eventually make it 0.5, right? Now, one common mistake which I am able to find here, you people didn't pay attention that H is an extensive property, right? So if at all you are multiplying here by 1 by 4, so the same effect should be done here also. So you should be getting 25 kilocalorie per mole here, 25 kilocalorie. So here the equation will be 2 by 4. Purposely I am writing like this. This is 3 by 4 B gas plus you are having 1 by 4 C liquid. So delta Ng in this case will become 1 by 4 and simply apply now delta H is equal to delta U plus delta NgRT. Majority of you forgot to do operation with basically that delta H. That's the reason you are getting closer to 99. Okay? So here it is 25 delta U plus 1 by 4 into 2 into 10 to the power of minus 3 kilocalorie. Temperature is 300. You will be getting this as 0.15. So delta U is 25 minus 0.15, which is nothing but 24.85 kilocalorie. Able to get it, everyone? Understood your mistake. Whatever operation you do here, same operation should be done with delta H because it is an extensive property. So we have decorated in the notebook that H is an extensive property, but we have to make use of it. Getting it? 24.85 is absolutely correct answer. There is no doubt about it. So those who are getting something different than that, make sure that you are checking. Now let us move on towards the next segment of this chapter. You are having here thermochemistry. Now to understand thermochemistry, simply break this into two terms. One is chemistry, which involves chemical reaction. Thermo related to heat here, right? So the thing is, and we are reading this thermochemistry in physical chemistry portion of chemistry. So we can say it is the branch of physical chemistry that deals with the study of energy changes which are involved in any chemical reaction. That is only your thermochemistry, right? So I'm writing here branch of physical chemistry, branch of physical chemistry that deals with study of energy changes in a chemical reaction. Now next is, let us go for thermochemical equation. Now when it comes to thermochemical equation, suppose I am writing a simple equation here, carbon solid, O2 gas giving you CO2 gas, and for this delta H is minus 94 kilocalorie per mole. Now the thing is, you don't have to remember these values which I am writing. Simply if at all somebody asks what is the thermochemical equation, so a chemical reaction in which Physical state of substances should be mentioned, and also whatever is the amount of heat released or absorbed, that should be mentioned. Getting it? That's only your thermochemical equation. I hope it is clear. I'm not writing the definition here. I made very clear. Physical state mentioned, along with that, whatever is the amount of heat absorbed or released, that should also be mentioned. That is only your thermochemical equation. Getting it? Now, let us go further for types of reaction. We basically have two types of reaction here. One is exothermic reaction, and the another one we are having endothermic reaction. So in exothermic reaction, heat is liberated or absorbed. Exothermic, what is that? In exothermic reaction, heat is absorbed or liberated? Heat is absorbed or liberated? Kindly respond there. Liberated. Good. So we are just going to see how to interpret this, or what is the representation of it. Okay. So here reactant to product, they may write down Q kilocalorie amount of heat is liberated. Like reactant to product plus maybe 10 kilocalorie, 20 kilocalorie. So that is a representation that heat is released. And this is one old convention. According to new convention nowadays, it is more clearly stated like this: minus Q kilocalorie. Minus means heat liberated. Getting it? Similarly, you are also having endothermic reaction. And in endothermic reaction, representation is reactant to product minus Q kilocalorie. And here you are having reactant to product delta H is equal to plus Q kilocalorie. Plus is telling you heat absorbed. Heat absorbed. Right? Okay, now let us go for understanding the next term, which is heat of reaction, or else enthalpy change of the reaction. Or sometimes it is also simply known as enthalpy of the reaction. So suppose I am writing this equation only. You will be getting CO2 gas, and here it implies delta H. Delta H is minus 94 kilocalorie per mole. So what does it mean? It means that when 1 mole of carbon solid reacts with oxygen, the 94 kilocalorie of heat is getting liberated. So whenever you are carrying out a reaction, that reaction will be happening at a particular temperature and pressure. So can I say all the reactants and products are present under same temperature pressure condition? So during that time, whatever is the amount of heat liberated or absorbed, that is basically known as heat of reaction. So I'm simply writing one equation here, so I can write down the amount of heat absorbed or released in a reaction when all reactants and products are present under same temperature and pressure condition. That's what is heat of reaction. Hopefully you got it. It's very simple. Sometimes it is also known as enthalpy also, or else enthalpy change here. Now let us go for factors affecting heat of reaction. These are very basic fundamental which are learning today. First one is amount. Now suppose I am writing an equation H2 gas plus half of O2 gas giving you H2OL, and suppose delta H here is minus 68 kilocalorie per mole, right? Now we know that H is an extensive property. So if at all I multiply here this equation by 2, so everything gets multiplied by 2 here, I'll be getting 2H2OL, and delta H in this case will become double than the previous one. I'll be able to write down this as minus 136 kilocalorie per mole. So I'm saying why it is happening. since H is an extensive property, so delta H of the reaction will vary according to the amount. So I'm writing the reason here so that you understand. Is there any confusion? And time and again I'm telling you, you don't have to remember these data. Is this point clear? Write this down so that we can proceed to the next one. Or else from the QR code later on you can write it. Niharika, at present I cannot go to the previous slide, but later on you can ask me, I'll share the slide. Second one, you are having basically physical state. Suppose I am having H2 gas plus half of O2 gas. It is forming H2OL. Delta H for this is minus 68 kilocalorie per mole. But if at all I go for H2 gas plus half of O2 gas, it is forming H2O gas. Delta H is found to be minus 57 kilocalorie per mole. Now if you carefully observe, in one I am making liquid, in another one I am making gas. Now do you agree the physical state of H2O liquid is different than the physical state of H2O gas? Right? Their physical states are different, and we know that the kinetic energy of a gaseous molecule will be more as compared to kinetic energy of a liquid molecule there. Right? In the sample, I am talking about the sample of water, I am talking about the sample of gas. So the kinetic energy is going to be different, and hence their internal energy is going to be different. Right? Because you know that internal energy is a summation of kinetic energy and potential energy of all the particles present in the system. So if internal energy is different, do we know that internal energy is related to enthalpy? Because H is equal to U plus PV. So if internal energy is differing, and hence the enthalpy will differ and the heat of reaction will differ. Is this point clear? Now another thing is, if at all we are stopping at H2O liquid, then 68 kilocalorie is released. But if at all I have to go up to H2O gas, then less amount is getting released. What could be the reason? The thing is, from H2O liquid to H2O gas, you need to supply some amount of heat so that it get converted, because it is endothermic process. So what happens? We reach up to liquid, 68 kilocalorie is about to get released, but the thing is, some amount, that means 11 kilocalorie is utilized for the conversion of liquid to the gas. That's the reason you are liberating less amount here. Simply focus on the magnitude, because it is liberating here. 57 is lesser than 68. Do not apply maths here, that minus 57 is greater than minus 68. Getting it? So I'm writing here, substances in different physical state, have different internal energies, hence their heat of reaction may vary. Right? Now, let us go for the next one, which is on the similar line, which is allotropic form. Suppose if I ask you what are the two allotropic forms, in fact two very common allotropic forms of carbon, one will be graphite, another will be diamond. We are basically studying their combustion reaction here, suppose. So carbon diamond and carbon graphite I am going for, plus O2 gas, here also plus O2 gas. It is going to give you CO2 gas. Here also it is going to give you CO2 gas. Now delta H here is found to be minus 94 kilocalorie per mole. Again I am saying you don't have to remember these delta H, and here it is minus 97 kilocalorie per mole. Now do you agree, in graphite and diamond the bonding is different here? If bonding is different, that means what? Their potential energies are different. Potential energy is different means internal energy is different. And if internal energy is different, that means enthalpy is different. And hence their heat of reaction is going to be different. That is the reason different amount of heat is getting liberated when different allotropic form of an element is reacting. Is there any doubt to anyone? So I'll write down here different allotropic form of an element have different internal energies, hence their heat of reaction may vary. I hope there is no doubt about this. Now let us go for the next point here, which is methods of measurement. Now, do you agree that heat is a path function, right? If heat is a path function, that means it will depend upon in which way I am measuring the heat, or else for which process I am measuring the heat. That means whether I am measuring the heat at constant pressure or else I am measuring the heat at constant volume, because I know that heat exchanges at constant pressure is delta H and heat exchanges at constant volume is delta U. So that's how your enthalpy is depending on the method of measurement. So I'm writing, since heat is a path function, so delta H of reaction may vary depending upon process. So I'm writing some general formula here which you already know. QP is delta H, QV is delta U. A general formula we know, delta H is equal to delta U plus delta PV. Remember, this was the main formula which we have written, and then if the pressure is constant, P delta V, if volume is constant, V delta V, both are changing, then delta PV, P2 V2 minus P1 V1. So you can write this, and if at all it is having some gaseous species, so I'll say for gaseous reaction, remember we have written delta H is equal to delta U plus delta Ng RT. So we are just writing a general information here, nothing more than that. And the last point here is, fifth one, temperature. Now, do you agree that when we change the temperature, internal energy of the substance changes? Right? Do you agree when we change temperature, internal energy changes or not? Does it change? Does it change or not? Yes, it changes. So accordingly, if internal energy changes, your enthalpy also changes. At present, I am giving you just one or two formula here. Please write them as a formula only. Later on, we'll solve numericals based on that. Okay, good. So you can write down here delta H2 minus delta H1 upon T2 minus T1, that is equal to delta NCP. So this delta H1 is change in enthalpy at temperature T1. Delta H2 is change in enthalpy at temperature T2. Right? Simply at present write down them as a formula. Delta U2 upon delta U1, this T2 minus T1, that is equal to delta NCV. Both of them, they are known as Kirchhoff's equation. And here it is coming from delta H is equal to NCP delta T, delta U is equal to NCV delta T. So delta U1 will be change in internal energy at T1 temperature. Delta U2 will be change in internal energy at T2 temperature. Right? So do remember, if temperature changes, so because of that internal energy changes, and because of that enthalpy changes, and hence delta H of reaction changes. Getting it? So up to this is your syllabus for this examination, and I am telling you that phase transformation, need not worry, that will get covered up little bit later on as the process is going on. Are you able to understand? So there should not be any confusion about whether that is part of the syllabus or not. Purposely I have not completed that. Reason being, the sequence in NCRT for some of the things are here and there. So for that purpose, I'll take it little bit later, but eventually it will get covered. Need not worry about it. Okay. So wish you all the best for your test, and I'm sharing the QR code here. Yes, QR code, it is coming. Are you able to see on the board? It is preparing to export. Scan it. Done scanning it. You can practice that, beta. Kavita, you can practice. Thank you and have a nice day.